Well, can you talk with this side? Okay. Okay, somebody tell me how to do it. Who would like to tell me how to do it? It's you. How do you do it?
Sin mu equals I3 plus.
Okay. Let u be x cubed plus 2, right? And then du dx is going to be what? 3x squared, right? So then what do you get here? In terms of switching it to u, you get cosine u du,
Yeah.
right? Okay. So of course you get sine u plus c, and so the answer is sine x cubed plus 2 plus c. Okay. Everybody all right with this? It's pretty simple. It's a common way of simplifying your integral so that you can evaluate it. So that you can so you can evaluate it. Okay. So what's really going on here? What's really going on? What's really going on here? Right. The thing is that right. Let's say it like this. What we're saying is that if we see something like f prime g of x, g prime x dx, right? If we see something like this, right, then it's legitimate to rewrite this as the integral of u f prime u du. F prime u du, right? So you say let u be g of x. Okay, and it's what we're saying is that it's okay. If we see anything like this, it's perfectly fine. We can just rewrite it like this, and then evaluate, right? And evaluate, right? What's going to happen? We're going to get f of u plus c. In other words, f of g of x plus c. Right. That's really what's going on in all of these examples, right? In all of these examples, we have the same thing, right? You have some function inside some other function, and then you have the derivative of that interior function, right? In other words, the chain rule, right? So this is just all this is saying is that we can do this because of the chain rule. Okay. Right. So why is it legitimate? Why is it legitimate? because the chain rule says so. The chain rule says that the antiderivative of this is just going to be f of g of x plus c. Right? Right, the chain rule says that the answer is this, and that's what we get if we do it this way. Right? If we do this substitution, that's the answer we get. Right? So because of the chain rule, it's okay. Use substitution is all right to do. Even though, I said it's crazy to talk about, remember we had something like this. It's crazy to think you can multiply through by dx. Right? This is not a fraction. Right? This is some sort of limit. This is a limit. Right? It's not some fraction. But even though that's sort of, theoretically, doesn't make sense, it's okay to do it anyway because we're going to get the right answer. Right? The chain rule tells us that doing this will give us the right answer anyway. So it's all right to play this game. So use substitution is basically just the integration version of the chain rule. So, like in the rules of differentiation, right? We have the chain rule, and that turns into rules of integration, turns into use substitution. So these things correspond. Okay, so that was for getting indefinite integrals, and now we're going to talk about definite integrals. So again, same topic basically. Use substitution for definite integrals. Use substitution for definite integrals. Okay. So again, we'll start off with an example. If I say, I'd like you to take the definite integral from 1 to 2 of, say, t squared minus t to the 5th, 2t minus 1 dt. Okay. One thing you could do is just use the method that we just developed, right? You say, well, so one method. Find the antiderivative using use substitution. Then evaluate the difference at endpoints. Right? Then evaluate the difference at the endpoints. Right? Okay. Now you just say, well, look, let's do use substitution on this guy. Right? You take u to be t squared minus t. Right? du dt is going to be 2t minus 1. Then this thing is going to be rewriting it u to the 5th du, so we get u to the 6 over 6 plus c, right? Which is t squared minus t over 6. Oops. T squared minus t squared minus t to the 6 over 6 plus c. Right? So you figure out the antiderivative, right? So 1, figure out the antiderivative, and then 2, evaluate the difference, right? So part 2, you say, okay, then I'm going to evaluate the difference from 1 to 2. Okay? So I get 2 to the 6 over 6 minus 0. Right? So 2 to the 6 over 6. Okay. So that's one method. Another method. Okay. So you go like this. You say adjust the domain of integration. So properly adjust the domain of integration. Okay. So you have here we've got this thing, t squared minus t to the 5th, 2t minus 1 dt. I'm going to switch it to, I'm going to again I'm going to use u as t squared minus t, right? So here I'm going to get u to the 5th du, right? But I'm going to do it over a different range of integration, okay? I'm going to say, so when t is 1, u is 1 squared minus 1, that's 0. Okay. When t is 2, right? When t is ranging from 1 to 2, right? When t is 1, u is 0. When t is 2, u is 2. Okay. So I get another definite integral, but with an adjusted range of I've adjusted the interval of integration. Okay. And what do you get? U to the 6 over 6 from 0 to 2. And what's that? 2 to the 6 over 6 minus 0 again. Okay. So there are two ways you can do this. You can just go straight forward using the previous method, find the antiderivative, and then evaluate the antiderivative between the endpoints, the Fundamental Theorem of Calculus. Or you can be a bit smarter, and just a little bit smarter, it's not that much smarter. And instead of switching back, you can keep the integral in the u form. You can keep the integral in the new variable, but you have to integrate between a different range of integration, right? Because as t ranges from 1 to 2, it's not the same as u going from 1 to 2. U is going to be between 0 and 2. Okay, so you have to adjust the domain of integration. Okay. So again, let's do a couple more examples to illustrate. Okay, so more examples. If I say I'm taking the integral of e to the x over 1 plus e to the x squared dx, right? What should I take as my u? What should I take as my u? Chen Jing. E to the x? You could do that, I think. You could either way, 1 plus e to the x, or in fact, e to the x would also work. 1 plus e to the x is a little bit easier, but e to the x would work fine. Let's do 1 plus e to the x because it'll be just a tiny bit simpler. Okay, du dx is going to be e to the x dx. Oops, e to the x. Excuse me. Right. And so what is this going to be? It's going to be the integral of u to the minus 2 du, right? And what's going to be the range of integration now? Well, when x is 0, u is what? 2. And when x is 1, you get 1 plus e. Right? Okay. So, right? And then, so we integrate this thing, we get u to the negative 1, negative u to the negative 1. Right? So negative 1 over u, evaluated between 2 and 1 plus e. And you get negative 1 over 1 plus e minus negative 1/2. Or if you felt like it, right, you could, right, if you felt like it, you could switch back at this point, right? You got negative 1 over u, u is 1 plus e to the x, right? And you evaluate that between 0 and 1, right? Or switching back, right? You get this, right? So this is going to be negative 1 over 1 plus e minus 1 over 2, right? And you get the same thing. Okay. Which way do you like? Which way do you like? I'm just curious. Do you like to figure out the antiderivative and then switch back and then switch back to the original domain and then evaluate? Or do you like to adjust the domain and stay with the new variable and evaluate? Which way do you like? Doesn't matter. How many people like the stay with the antiderivative and then switch back? How many people like the switch the domain of integration? Okay, so and then I think maybe everybody else doesn't like either way. The rest of you maybe don't like any way. So there's some, okay, so it seems like some people like the second way better. I think the second way is better. But it doesn't really matter. It's, you do the same thing anyway. Okay. Okay. So here, let me ask you to do one as practice. The integral of 1 minus cosine 3t sine 3t dt. Okay. So take 1 minute and do it. Okay, turn to somebody nearby and check what you're doing. Okay, please talk to somebody next to you to see if they got the same answer. Okay, who would like to talk about it? Who would like to give it a try? Me, Peyton? How about you? Would you like to try? What will you take as your U? One minus sine 3t? This is cosine, right? So let's take u to be 1 minus cosine of 3t. Right? And then when you differentiate that, what do you get?
3 sine 3t.
Right? You get sine, you get negative sine 3t times 3 by the chain rule, right? Right? And so du is going to be, whoops, why am I putting an x here? That doesn't make any sense. You get 3 sine 3t dt, right? Okay. So then changing this thing, we're going to get u and then 1/3 of du, right? U and then 1/3 of du. Right, and so, right, what's the range of integration? Somebody other than me, Pekka? Somebody else? How about you? I don't know your name.
1 and 0.
1 and 0? Okay, so let's see, when t is 0, we're going to get cosine of 1 minus cosine 0, right? So that's going to be 0, right? And then when t is this, we're going to get cosine of 1/2. Well, that's 0, right? So we get 1 up here. Right? Okay. So you get u squared over 2, 1/3 of that between 0 and 1, right? And so you get 1/6, right? 1/6 is the answer. Okay. Okay, everybody all right? Any questions about this? We could do more. I have 10 more examples, but I think there's no point in doing more examples. That's probably enough examples, right? Okay. So let me just sort of formalize formalizing the method. Okay, I'm going to state it formally. Okay, so let f be continuous on AB. Then the integral from a to b of f g of x, g prime x dx is the same thing as the integral of f u du from g of a to g of b. Right? That you let your u be g of x, right? When x is a, you're going to get g of a. When x is b, you get g of b. Right? So this is just stating formally what we've been doing in all the examples. Okay. Well, why can we do this? Well, because if f is any antiderivative of little f, then the derivative of this composition is f prime g of x, g prime x, right? which is f of g prime x. But then, if we look at the integral, I think I'm going too fast. Let me slow down. Let me slow down. Okay. So, why is this true? Why is this true? You say, well, look, suppose we take any antiderivative of little f. Okay. Then you notice that that antiderivative composed with g is an antiderivative of the integrand. Right? Is an antiderivative of the integrand. Right? Because when you differentiate it, that's what you get. When you differentiate this guy, then you get the integrand. Right? Okay, but then this is going to be the antiderivative between a and b, right? By the Fundamental Theorem of Calculus. Right, which is f of g of b minus f of g of a. Right, but that's the same thing as the integral from g of a to g of b of little f. Against whatever variable you like, using whatever variable. Okay. So what we're saying is that it's okay to change. It's okay to switch the variable to this other variable, but you have to adjust the domain of the range of integration. You have to adjust the range of integration. Right? Why? Well, look, when you do it, you see that you have to adjust the range of integration changes. Right? If you look at this integral, well, that's equal to this, that's equal to this, that's equal to this, and the range of integration changes from g of a to g of b, rather than a and b. People always ask, students always ask, why can't I just use the original range of integration? But you see that you can't do that. Right? It has to change. Okay. Do people want to stand up for a minute? You can take a break for a minute. Yeah. Take a break. Take 1 minute break. I think people are getting tired. Stand up, walk around. So what are you going to do? Are you also there you go.
For a while.
Are you Is everyone here? No, we lost 2 people. Okay, while we're waiting for the people to come back, let me ask if this is clear. Does anyone have questions on this thing, on this part here? Does anyone have questions on this part? Right. Okay, let's get started, please. Let's get back. Let's going again. Okay. Okay. So let's see. That was. Okay. So the next technique is called technique number 2 is called integration by parts. Integration by parts. Okay, and just like how the previous technique, the U substitution, corresponded to the chain rule. This one is also going to correspond to a rule of differentiation. So this is the sort of analog of the product rule. The analog of the product rule, right? So recall the product rule, right? If I'm taking the derivative of a product, right? So I have 2 functions, u and v, and I take their derivative, well, I'm going to get u of x v prime x plus u prime x v of x. Right? That's the product rule. Right? So another way of saying that is that, that the antiderivative of u times v, I'm sorry. Yeah. That the antiderivative of u v prime plus u prime v is u v. right? Plus a constant. Right? I'm just saying the same thing, right? The derivative of the left side is the right side. In other words, the antiderivative of the right side is the left side, right? So I'm just saying the same thing twice. Okay, is that clear? That I just written the same thing 2 times over? Double. Okay. Okay. Now, you notice that this actually gives you something. It says that, let me write it like this: u of x, v prime x, dx, plus u prime x, v of x, dx, equals u of x, v of x plus c. Okay. So I'm going to break this thing into two antiderivatives, right? 2 indefinite integrals, and then I'm going to rearrange it. Okay. So the integral of u v prime equals negative the integral of u prime v plus u v